All right, so the next big topic is rotational torque. So this sort of connects with forces and dynamics, right? So a net torque is going to cause angular acceleration. And the equation here is net torque equals moment of inertia, which is sort of like mass, except it accounts for how mass is distributed, times angular acceleration. So that's very similar to net force equals ma. All right, so a greater moment of inertia will lead to less angular acceleration given the torque is the same, and vice versa for less moment of inertia. And here's a very nice diagram that sort of shows you how moment of inertia changes based on the concentration of masses. And here's another diagram depicting a really nice example, and we'll get to it more when we talk about rotational energy. But this is where we're talking about what is causing that net torque. And because of the way the equation is set up, if I can find it right here, torque is equivalent to force times r sine theta. So if you apply that, there's a 2016 FRQ on this. I did a video on it where I found that the force of friction is the one that actually causes the torque. So if you're wondering why, definitely go check out that FRQ video. Fg and Fn do not cause a net torque here due to that equation. And so you want to draw the forces from the position in which they act, especially for free body diagrams. All right, so now let's just talk about the general torque and how it works. So torque is not a force essentially, but it's sort of is the thing that causes objects to rotate around a axis or pivot. So it's sort of like a collection of all forces and then is just a way to represent them. So torque is equivalent to force, which is just the force exerted, times r, which is the distance from the pivot that the force is applied. That can also be interpreted as radius. And then in some examples, you can use sine theta, and theta is measured in respect to the radial line. And here's a wrench, and it's showing you how the only component of the force that is perpendicular to the radial line, which is r, is the one that causes the torque. So you can observe in two ways here. If you use this pink angle, you'd have to use cosine to find that perpendicular component. And if you use this green side over here, you use the sine theta. Alrighty, so torques in equilibrium. So here is a example of that where we can see we have a guy standing on one side of this plank thing, but the plank thing, since it is off its center of mass, all of its mass acts at the center of mass. So it's not depicted nicely here, but there is a 100 Newton torque that acts clockwise in this problem we can see here. And so the torque that the person is exerting is going to be in the other direction, counterclockwise. And that's going to be the force of gravity. And so here is the equation that shows you how it's being represented in this example. All right, so now let's talk about rotational energy. So for rotational energy, it is equivalent to, when you talk about kinetic rotational energy, it's equivalent to 1/2 times moment of inertia times angular velocity squared. So that's pretty similar to translational or linear kinetic energy, which is 1/2 mv squared. You can see how there's correspondence between moment of inertia and mass, and then angular velocity and linear velocity. So here we have a ball object thing that is rolling down. So the force of friction, like we talked before, is going to be causing that angular acceleration. And since it points clockwise, that angular acceleration will be clockwise as well. And since linear velocity is already pointing in the clockwise direction, it'll be speeding up and getting faster. And so it starts with the gravitational potential energy, assuming it's released from rest, and that's going to be converted to both kinetic translational energy as well as kinetic rotational energy. Now it's a different story when the ball is rotating up, because now the force of friction is pointing upwards, and so it's going to be causing a angular acceleration counterclockwise. And because the ball is rotating upwards, right, there's that initial angular velocity going up, but that is pointing clockwise, whereas the force of friction causes that angular acceleration to be counterclockwise. And so angular velocity and linear velocity will be decreasing. And then for energy, it would be kinetic energy translational plus kinetic energy rotational to start, and that's all converted to UG, assuming the ball stops somewhere at the top. All right, so the final topic is angular momentum. So angular momentum, similar to linear momentum, is a vector. The symbol for it is L, and these are the units, kg times mass squared over seconds. So if there is no external torque, angular momentum changes. You can see the equation for that, where torque exerted over time is equivalent to the change in angular momentum. So if there's no torque, there's no change in angular momentum. So angular momentum would be conserved. Now regarding collisions, so linear momentum, we talked about collisions there, so that still applies to angular momentum. And so if there are no external forces on a system in inelastic collisions, then the total momentum is conserved and kinetic energy is conserved as well. And then for inelastic collisions, only momentum is conserved and kinetic energy is lost. And for perfectly inelastic collisions, it's going to stick together, and that is the greatest loss in kinetic energy, which you can calculate. And just some final equations to note down here is the angular momentum of a point mass is just mv. Note that is change in linear momentum times radius. And then we have our standard angular momentum equation, which is equivalent to moment of inertia times angular velocity. And then the same principles of conservation of energy, conservation of momentum, conservation of now angular momentum. You can see that if there is no net torque, then it would balance out. Just like how we talked about mv equals mv, now we have moment of inertia times angular velocity is equivalent to the final moment of inertia times final angular velocity. All right, so the second thing is gravitation. So essentially, objects are going to be orbiting a shared center of mass. And the first part of this is Newton's law of gravitation. So it's very similar to Newton's third law, actually. You can see here that the gravitational force that planet 1 exerts on planet 2 is equivalent to the gravitational force that planet 2 exerts on planet 1. And they're going to be orbiting this center of mass in between them. In the equation that represents that gravitational force is equivalent to the gravitational constant times mass of 1 times mass of 2 divided by r squared. So r does not represent the radius, although sometimes it can. Instead, it's the distance between the centers as seen here. So something to note here, and we'll get below when we derive for the orbital velocity, is that centripetal force, the Fg is the centripetal force for orbiting satellites, right? Because when you're drawing your free body diagrams, the only force acting towards the center for those satellites is the force of gravity, because it is the shared center of mass between that planet and that satellite. All right, so now let's talk about how to calculate little g for planets. So we know that little g on Earth is negative or 9.8 meters per second squared. So how do you calculate that for other planets, right? So the equation for that is just the gravitational constant times the mass of that planet divided by its radius squared. So here's an example for Mars. We take the mass of Mars, we multiply it by the gravitational constant on the top, and then the radius of Mars, we square it, and we find that the little g for Mars is 3.77 meters per second squared. Here's a very nice cheat sheet regarding Newton's law of gravitation. We can see that the effective masses on the left side and the effective distance on the force of gravity. So this is just a nice way to map out the different effects. I won't go through it in detail. You can take a screenshot if you would like, but you can figure all of this out just by using the equation. But just having these types of relationships in your mind, maybe even memorizing them at some point, will definitely be useful and save you a lot of time on, say, like multiple choice questions that want you to compare the effect of increasing mass or increasing distance, etc. And our final topic today is gravitational potential energy. So when we are on Earth, there is a constant gravitational field, which is why we can use the equation gravitational potential energy equals mgh. However, when there's a non-constant gravitational field, we're going to have to use this other equation, which is gravitational potential energy is equivalent to negative gravitational constant times mass of 1 times mass of 2, and then divided by r
distance between objects. So it's very similar to Newton's law of gravitation, except the r is not squared and it is also negative. So you're going to use this to find the gravitational potential energy between two objects or systems.
Alrighty, so that does it for this review. Hopefully you guys learned something. If you have a question, drop it down below, and thank you for watching.